Hello children. In this session, I am going to discuss the topics of electrical capacitance. Electrical capacitance is our fourth section of electrostatics and it is our concluding section of the unit electrostatics. So before getting into the concepts of electrical capacitance, I am going to discuss the behavior of a conductor in an electric field. I am going to discuss the behavior of a conductor in an electric field. So one by one we are going to discuss the characteristic behavior with reasons. So the very first characteristic property or behavior of a conductor is, inside the conductor the electric field is zero. So what is the first characteristic property about the conductor I am going to say is, inside the conductor the electric field is zero. So let us discuss the reason behind it. So to show that, I am going to assume a conductor that is subjected to an electric field, uniform electric field. I am going to keep a conductor in a uniform electric field. Now, when I am going to keep the conductor in a uniform electric field, already you know a conductor contains free electrons. A conductor contains free electrons. So when this conductor is subjected to the electric field, I am going to say what happens due to the electric field. The free electron starts drifting towards the positive plate till equilibrium. This means, what is equilibrium? Equilibrium is basically the static condition. Equilibrium is basically the static condition. So what I am going to say once again, due to the electric field, what happens to the free electron? The free electron starts drifting towards the positive plate till equilibrium, that is a static condition is reached. So what I can assume, a redistribution of free electron occurs. A redistribution of free electron occurs. So what I can say, the face of the conductor that is closer to the positive plate becomes negative. Similarly, the face of the conductor towards the negative becomes positive. So once again, due to the redistribution of free electrons, what happens? The face of the conductor that is near to the positive plate becomes negative, and the face of the conductor that is closer to the negative plate becomes positive. So you are able to see an internal electric field is also produced. What I can say, due to this redistribution of charges inside the conductor, what I can say, it results in an internal electric field inside the conductor. And what is the direction of that internal electric field? It is opposite to the applied electric field. You are able to see this is plus minus, it will minus plus. So ultimately, what is the nature of internal electric field due to the redistribution of charges inside the conductor is opposite to the direction of applied electric field. So under static condition, the distribution of free electrons is in such a way, is in such a manner that what about the internal electric field due to the charges cancels the applied field. Once again, the internal field, in a very simple language, the internal field cancels the applied electric field under static conditions. So ultimately, the net electric field inside the conductor is zero. Ultimately, the net electric field inside the conductor is zero. Now, we can think in another way. Let us suppose that there is non-zero electric field inside the conductor. What I am going to assume is, let us suppose that there is non-zero electric field inside the conductor. So what will happen? If the electric field is non-zero, this means the free electron experiences a force. A free electron experiences a force, and ultimately it may not be in static condition, and that may result in an internal current inside the conductor, which is not possible. We know this. That results in an internal current inside the conductor. Now, in a nutshell, what I can say, if we are going to say that the electric field inside a conductor is zero, this implies that there can be no net charge anywhere inside the interior of the conductor. There can be no net charge anywhere inside the interior of the conductor. Now, I think this property is very clear. Once again, I am going to repeat the property. Inside the conductor, the electric field is zero. Now, I am going to get into the second property. So, what is the second property? What about the electric field at the surface of the conductor is always at right angles to the surface? What about the direction of electric field? Just outside the surface, the electric field is always at right angles to the surface. Once again, just outside the conductor, what about the direction of electric field? The electric field is always at right angles to the surface. So let us explore the reason behind it. This means there cannot be any tangential component of the electric field at the surface. Ultimately, what do you mean by this? The electric field is always perpendicular to the surface. What do you mean by this? This means there cannot be any tangential component of electric field at the surface. Let us suppose that if there is a tangential component of electric field at the surface, what will happen? Ultimately, the free charges will experience a force. It moves. This means it may not be in static condition, and that may result in surface current. And this is the reason that whenever I am going to speak, the electric field enters or leaves always at right angles to the surface. Geometrically also we can explain the same fact. So let us suppose that this is the surface. The pattern will be like this. Similarly, I am going to draw for here. The entering and the emitting will be always perpendicular to the surface. This is our second characteristic property. I am going to get into the third characteristic property. When a conductor is charged, the acquired charges only resides at the surface of the conductor. Once again, when I am going to charge a conductor, the acquired charges only resides at the surface of the conductor. So how we can justify this? Obviously the justification is very simple. If I am going to consider a conductor like this, I am going to assume, say this is a conductor having charge Q. I am going to draw a Gaussian surface immediately inside the conductor. Now, already we know inside the conductor the electric field is 0. What do you mean by this? That means the flux through the Gaussian surface should also be 0. Once again, the flux through the Gaussian surface should also be 0, and according to Gauss theorem, if flux is 0, there cannot be no charge inside the Gaussian surface. So ultimately, what about the charge you are going to supply? It always resides at the surface of the conductor. This is our third property. Get into the fourth characteristic property. The entire conductor, including its surface, is at constant potential. So how we can justify this? Obviously, I am going to assume 2 points inside a conductor, say A and B. I am going to move a test charge Q0 from A to B. Obviously, no work will be done because the electric field inside the conductor is 0. Similarly, I am going to consider 2 points on the surface, say A and B. If I am going to move a test charge Q0, here also there will be no work done. The reason is there is no tangential component of electric field at the surface. So ultimately, what about this? All things are possible if the entire conductor is at constant potential and has the same value at the surface. Once again, to prove the entire conductor is at constant potential, what are the two facts I am going to explain? I am going to assume a test charge is moving from point A to B inside the conductor. No work will be done since the electric field is 0. And also no work will be done in moving a test charge on the surface, say from A to B. Here also we are going to say there is no tangential component of electric field exists at the surface. So this is only possible if we are going to say the entire conductor is at constant potential and it should have the same value at the surface also. So these are the 4 important characteristic properties related to conductor in an electric field. Now we are going to get into the fifth, the last property. We are going to derive an expression for electric field at the surface of the conductor. I am going to derive an expression for electric field at the surface of the conductor. So ultimately at the last, we are going to get E is equal to sigma by epsilon naught. If I am going to write in vector form, it will be like this. Once again, what is the fifth characteristic property? We are going to derive an expression for electric field at the surface of a conductor. What about the expression of electric field at the surface of a conductor is E vector is equal to sigma by epsilon naught n cap. So for this, I am going to assume a conductor. I am going to assume, say, a irregular shaped conductor having uniform surface charge density. You know, surface charge density is sigma. Obviously, you know, the charges will be uniformly distributed at the surface only. The charges will be uniformly distributed at the surface. Yes. Now, I am going to consider a point P very closer to the surface. I am going to consider a point P very closer to the surface. What is my explanation? The point P is so closer to the surface that what will be the electric field I am going to get at P will be the same for the surface. So to find the electric field at P, what I am going to do, I am going to assume a cylinder. I am going to assume a cylinder around P with upper face through P, that is outside the conductor, and the lower face, say Q, is inside the conductor. The lower face is inside the conductor. Obviously, you know the electric field acts normal, and I am going to represent like this. So once again, I considered a conductor with uniform surface charge density sigma. My aim is to find what is the electric field at the surface of the conductor. To get the value, I am going to assume a point P which is very closer to the conductor, but for convenience sake the point P is a little far, but in practice the point P is very closer to the conductor, where obviously what is the logic we are going to speak is, since the point P is so closer to the conductor, what will be the electric field we are going to find at P will be the same for the surface. So to get the value of electric field, I am going to consider a Gaussian surface. The Gaussian surface is a cylinder with upper face through P is outside the conductor, and the lower face Q is inside the conductor, and you know the electric field is normal to the plane. Now, what will be the small flux? Obviously, you know, since the electric field inside the conductor is 0, there will be no contribution of flux for this part. So the only contribution of flux is through the upper part. So what about the small flux? I can write as d phi is EDS. D phi is EDS, and I am going to mark it as equation number 1. What according to Gauss theorem? You know, according to Gauss theorem, you know that is Gauss theorem is phi is q by epsilon naught, but we are going to speak for a small value, so I am going to write as d phi is small charge dq by epsilon naught. Actually it comes from phi is equal to q by epsilon naught. It comes from phi is equal to q by epsilon naught. So I am going to write d phi is dq by epsilon naught. You know what is q by a? So q can be written as sigma a. Sigma a is, we assumed area as ds. So q can be written as sigma ds. Put it back. So what I am going to get is d phi is equal to sigma ds by epsilon naught. I am going to mark it as equation number 2. One I am getting from the concept of electric flux. One I am going to get from Gauss theorem. Equate the two. Since the LHS are equal, I can equate the two. So what I can get is E ds is equal to sigma ds by epsilon naught. Ds cancels. So what this implies, E is equal to sigma by epsilon naught. If I am going to write in vector notation, it will be E vector is equal to sigma by epsilon naught n cap, and you know n cap is the outward drawn normal. N cap is the outward drawn normal. Once again I am going to explain the entire derivation. Obviously, what is our fifth characteristic property of the conductor is the electric field at the surface of the conductor is given by sigma by epsilon naught n cap. We are going to derive this. For this, I considered a conductor with uniform surface charge density sigma. Next, I considered a point P which is very closer to the surface where I want to get the electric field, and ultimately I am going to speak the point P is so close to the surface that what about the value at P will be the same at the surface. So to get the electric field, I constructed a Gaussian surface. Gaussian surface is a cylinder. Obviously the outer face of the cylinder is, that is P, is outside the conductor, and the inner face Q is inside the conductor. Now I am going to speak about the flux. You know, since inside the conductor the electric field is 0, there will be no contribution of flux. So flux is only through the upper face. I am going to assume the area is ds. What about the area? I am going to assume is ds. So what about the flux? Can be written as, you know, EDS. D phi, what is a small flux linked with this upper face of the cylinder is d phi is equal to EDS. Why it is EDS? Because you know E and ds are parallel. For that I am writing d phi is equal to EDS. Mark it as equation number 1. Second, according to Gauss theorem, you know phi is q by epsilon naught. Just change it. It is d phi and dq. So d phi can be written as dq by epsilon naught. So what is dq? dq can be written as sigma into ds. It's ultimately from the surface charge density formula I am writing, equating 1 and 2 to get the electric field at the surface is sigma by epsilon naught. Once again I am going to explain all the 5 characteristic properties of a conductor in an electric field in a brief way. So what was the first property? The electric field inside the conductor is 0. Always the electric field inside the conductor is 0. What is the second one? Just outside the surface, the electric field is always at right angles to the surface. Just outside the conductor, the electric field is always at right angles to the surface. This means the electric field enters or leaves always at right angles to the surface of the conductor. Third, when we are going to charge a conductor, the acquired charges only resides at the surface of the conductor. That was the third property. Fourth one, the entire conductor including the surface all are at constant potential. And the fifth one, what about the electric field at the surface of the conductor was E is equal to sigma by epsilon naught. Now with this I am going to get into the next topic, that is our electrical capacitance. We are going to discuss what is capacitance first. So capacitance, the word itself has a meaning. It is the charge storing ability of a conductor. What I can say, it is the charge storing ability of a conductor. So let us suppose that if I am going to consider a conductor, say this is a conductor and I am going to supply Q charges. I am going to supply Q charges. So what will happen? So ultimately its potential increases. Its potential increases. So what is the logic I am going to speak? If I am going to supply Q amount of charges to a conductor, what happens to its potential? The potential also rises gradually. So I can establish a linearity between these two variables, that is Q is directly proportional to V. This charge is directly proportional to the potential. Now you remove the proportionality constant. I am going to put a constant C. V. So what I am going to get is a very important formula, Q is equal to CV. In this entire chapter we are going to use this formula. Here C is the constant of proportionality we said, and it is capacitance. And it is capacitance. Now we are going to define the capacitance. What is capacitance? In two ways we can define. Just by shifting, C can be written as Q by V. C can be written as Q by V. So we can give words for this. So the electrical capacitance of a conductor is the ratio of charge on it to its potential. It is the ratio of charge on the conductor to its potential. It is one way of defining the electrical capacitance. One more way, what I am going to assume, let V is equal to 1 volt. V is equal to 1 volt. So what about C is equal to Q? What I am getting from this is C is Q. Once again, what is capacitance? Is the ratio of charge to its potential. In another way, I am going to assume that V is equal to 1 volt. This means C is equal to Q. Once again, we can play this in words. What about this? The electrical capacitance of a conductor is numerically equal to the charge. Electrical capacitance of a conductor is numerically equal to the charge that raises the potential of conductor by 1 volt. That raises the potential of the conductor by 1 volt. That equivalent charge can be termed as capacitance. So these are the ways in which we can define electrical capacitance. Now the most important thing, on what factors the electrical capacitance depends. Already I said in while discussing the first chapter also, on what factors the constant of proportionality depends. You should take care of those things because it will be helpful while dealing with small questions. Now the very first, it depends upon the shape of the conductor. It depends upon the shape of the conductor. Number two, it depends upon the dimension. It depends upon the dimension. It depends on the nature of the medium. It depends upon the nature of the medium in which the conductor is placed. It does not depend on the nature of the material of the conductor. It does not depend upon nature of material of conductor. This is very important one, you should know. On what factors the electrical capacitance depends? The very first is, depends upon the shape of the conductor, depends on the dimensions of the conductor, depends upon the nature of the medium in which the charges are, in which the conductor is placed, and it does not depend upon the material of the conductor. It does not depend upon the material of the conductor. Next, I am going to speak what is the unit of electrical capacitance. Unit of electrical capacitance is farad. Unit of electrical capacitance is farad, and I am going to give a symbol capital F. Going to give a symbol capital F. Now we can define 1 farad just like we used to define unit value. Similarly, I can define a unit value. So I can define 1 farad. So I am going to use this formula. So in place of C, I am going to put 1 farad. In place of Q, I am going to put 1 coulomb. In place of V, I am going to put 1 volt. So 1 farad can be written as 1 C by 1 V. So how we can put in words? So the capacitance of a conductor is said to be 1 farad. The capacitance of a conductor is said to be 1 farad if 1 coulomb of charge raises the potential of the conductor by 1 volt. If 1 coulomb of charge raises the potential of the conductor by 1 volt, and that becomes the definition for farad. Similarly, while doing numerical, we come across microfarad and picofarad. You know, microfarad stands for 10 power minus 6 farad and picofarad stands for 10 power minus 12 farad. So these are the values that will be helpful while doing numerical. Now I'm going to define what is a capacitor. What we discussed till now is capacitance, electrical capacitance. Now we are going to give words for capacitor. So I think by the name itself, capacitor is a device. Capacitor is a device used to store large quantity of electric charges. Once again, what is a capacitor? Capacitor is basically a device that is used to store large quantity of electric charges. You know, a conductor, if you consider an ordinary conductor, it has also a small charge storing ability. So ultimately, it can also be termed as a capacitor, but we are going to discuss, before getting into the content, I am going to discuss what is the principle of a capacitor. What is the principle of a capacitor? Once again, capacitor is a device used to store large quantity of electric charge. On what principle the capacitor works, we are going to explain. For this, we are going to discuss two sections to understand the principle or the basic thing behind the capacitor. I am going to consider two different cases, and ultimately after the conclusion, we will be having a clear idea what about the principle on which the capacitor works. So what I am going to assume, I am going to consider a conductor, a metallic conductor, say A. I am going to consider a metallic conductor A, to which I am going to supply positive charges. I am going to supply positive charges. So what happens if the positive charges are continuously supplied? Its potential increases, and a stage comes when the potential reaches maximum. Once again, I am going to continuously supply the charge, positive charge to the plate A. So a stage comes when the potential becomes maximum. So once the potential reaches maximum, and if I am going to supply the charge, what happens to the charge? The charge leaks to the surroundings. The charge leaks to the surroundings, and that is my case. I am going to assume you are supplying the charge till there is a leakage of charge to the surroundings. In this instant, I am going to keep one more metallic conductor closer to A, and I am going to mark it as B. I am going to keep one more metallic conductor B, which is closer to uncharged metallic conductor, which is closer to A. Now you know a phenomenon of induction occurs. Opposite kinds of charges are induced. This means to the left face of B, negative charges will be induced. To the left face of B, negative charges will be induced, and to the right face, positive charges will be induced. Right face, positive charges will be induced. So now you can say what this negative charges tries to do with the positive plate. It tries to reduce the potential because they have a cancelling effect. It tries to reduce the potential. So, but what happens to the positive plate on this? Obviously, it tries to support the potential. It tries to support the potential. But ultimately, which has a greater effect? Since the negative plate is closer to this, it has a greater effect. So ultimately, the potential of the conductor A reduces by a very small amount. Potential of conductor A reduces by a very small amount. So ultimately, if the potential is reduced, you are going to supply that much amount of charge to make the potential as usual. So what happens to the charge storing ability of a conductor? It is slightly increased if I am going to keep an uncharged conductor closer to it. This is the first basic principle behind the working of a capacitor. Now I am going to speak the second instance. I am going to assume the same situation. Plate A is given positive charge. So this is plate A. Say uncharged plate B. The left face is negative. What I am going to do? I am going to earth connect plate B. I am going to earth connect plate B. Once I think if it is earth connected, what happens? All the positive charges, you know, this is positive. So all the positive charges flows into the earth. You know, all the positive charges flows into the earth. Why? Because it is repelled by the plate A. Because it is positively charged, all the positive will be flowing into the earth due to the repulsion of the positive charge plate A. But what happens to the negative charge? Negative charge stays in their position because they are attracted by the plate A. So ultimately, here there was dual effect. This negative tries to decrease the potential, this positive tries to enhance the potential. Ultimately, the potential reduces to a small extent. But here there is no effect of this positive, only negative has an effect to this plate. What happens to the potential? The potential reduces to a larger extent. The potential reduces to a larger extent, and once again, to make the potential as usual, large quantity of electric charge is to be supplied. So ultimately, the charge storing ability of the conductor is highly increased if I am going to keep an uncharged earth connected conductor closer to it. And this forms the principle of the capacitor. This forms the principle of the capacitor. So in a nutshell, what is a capacitor? Yeah, what is the principle of a capacitor? They are going to say, what I am going to say, it is an arrangement of two metallic conductors. Capacitor is basically an arrangement of two metallic conductors such that if one conductor is earth connected, the other conductor has the ability to store large quantity of electric charge. The other conductor has the ability to store large quantity of electric charge, and this becomes the definition of capacitor. Yeah, you can take it as a principle. Once again, I am going to repeat the principle or the what is capacitor. Capacitor is basically an arrangement of two metallic conductors, such that if one conductor is earth connected, the other conductor has the ability to store large quantity of electric charge, and this forms the principle of the capacitor. Obviously, there are two conductors you are able to see. These conductors are called coatings of the capacitor. What we are going to use a word called, these two conductors are termed as coatings. They are termed as coatings. Coatings may have different shapes. Accordingly, the coatings may be spherical. It may be cylindrical. The coatings may be cylindrical. Yeah, it may be plane. The coating may be plane. And accordingly, the capacitors are termed as spherical capacitors, cylindrical capacitors. It is not plane capacitor, it is parallel plate capacitor. Once again, if the plates are plane, what type of name I am going to give for that capacitors? It is called parallel plate capacitor. And in our syllabus, we are only going to discuss about the topics of parallel plate capacitor. Capacitance of a spherical conductor. Obviously, it is a simplest derivation. For that, we are going to start from this. Our aim is to find what is the capacitance of this spherical conductor. So, for this, what are the consideration? I am going to consider a conductor of radius r with charge q. Say this conductor is kept in vacuum or air. I am going to assume either it is kept in vacuum or air. So, you know, what is the charge that is at the surface can be assumed to be at the center also. Already we studied in Gaussian theorems also. What about the charge that is distributed at the surface? We can assume as if the charge is concentrated at the center. With that logic, I am going to assume the charge is at the center. Obviously, the charge is at the surface, but due to the symmetry, what I can assume is the charge can be supposed to be concentrated at the center. So, what will be the potential at a point P on the surface? What is the expression for potential due to point charge we derived? Na? V is equal to 1 by 4 pi epsilon naught Q by R. You know this formula, 1 by 4 pi epsilon naught Q by R. Obviously, this is the potential at point P, which is at a distance R from the center. I am going to mark it as equation number 1. Now, what is the formula for capacitance? Already I said, you know, Q is CV. So, what about C can be written as? Q by V. C can be written as Q by V, and I am going to mark it as equation number 2. So, I can put 1 in 2. What will happen, you say? Put 1 in 2. So, what happens? C is equal to Q by 1 by 4 pi epsilon naught Q by R. So, I think Q cancels off. So, what I am going to get is 4 pi epsilon naught R. So, what is the capacitance of a spherical conductor? Is 4 pi epsilon naught R. So, this is our final expression for capacitance of a spherical conductor. You know, C is in farad, R is in meter. What should be the units? C should be in farad and R is in meter. Obviously, farad is a very bigger unit of electric charge storing ability, that is capacitance. Now, I am going to speak about the symbol of capacitors, because while dealing with electrical circuits, we are supposed to draw capacitors. We are going to draw capacitors as a circuit element. So, how to represent capacitor? So, I am going to give you two denotions. Say, this is my first representation of capacitor. I am going to mark it as C. C is the capacitance. The second denotion The second denotation, it will be like this. Here also I am going to say it's a variable value. So what is the difference between the two symbols? If I am going to use a fixed capacitance, I am going to use this symbol. If I am going to use a variable capacitance, I am going to give this symbol. So these are the symbols of capacitors that we usually use while dealing with electrical circuits. With this, I am going to end my session. Take care of yourself. Stay home. Stay safe.